Hey everyone, Josh Tyson here with another episode of Invisible Machines. I am a contributing editor at UX Magazine, and I'm joined today by our resident AI visionary, Robb Wilson, who's the CEO and co-founder of OneReach.ai. Robb and I co-authored the best-selling book, Age of Invisible Machines, and this podcast is where we continue our explorations of agentic AI. Today, we're really excited to be talking with Bryan Catanzaro, the Vice President of Applied Deep Learning Research at NVIDIA. Bryan was instrumental in the adoption of GPUs for powering machine learning, which has effectively turned NVIDIA from a graphics processing hardware company into a $4 trillion AI powerhouse. Bryan joins us today to talk about his journey in AI and how the unique power structure at NVIDIA enables the company to routinely meet the moment in increasingly surprising ways. Robb has been following Bryan's work closely since a 2019 keynote, wherein Bryan made a plea to librarians at Stanford for help categorizing data in emerging large language models. And we get into that, but perhaps most importantly, Bryan explains how human hair might represent our first foray into technology. Now, customarily, we record the research calls that we have with our beautiful guests, and this is one of those rare cases where the research call itself was so interesting that we decided to go ahead and release it as an episode. The timing ended up being fortuitous as well, because we talked with Bryan right before their $4 trillion valuation, and as you'll learn in this episode, in true NVIDIA fashion, he's been heads down pretty much ever since. So let's get ready for a great conversation with a brilliant mind underneath a fabulous head of hair, Bryan Catanzaro.
We wanted to get super technical when we were prepping for this call. We were like imagining that you probably hear all kinds of comments about your hair on a regular basis. And we thought your hair is so epic that it doesn't even belong to you. We imagine that your hairdresser won't let you do anything without their permission. That it's like a joint custody thing.
That's funny. Now I'm feeling really self-conscious because I didn't do my hair this morning. You know, I just kind of.
It looks really good.
You think so? NVIDIA has the day off work today, and so I slept in and I didn't worry about my hair at all. But yes, I do spend a lot of energy on my hair. I've had it cut by the same person for 15 years, and she knows what she's doing.
Right. Joint custody.
And,
she's like, "What did you do? Don't ever take this to anyone."
Yeah. My wife is a hairstylist, and I used to help her manage a salon for a while, so I understand that relationship well.
It's important. And you know, I don't know exactly how important my hair has been to my career, but I think it's been really important. You know, I think that everybody is trying to get attention and trying to connect people, right? You work with what you've got. Everybody's got different things to work with, and I definitely work with my hair. So, you know, I have long theories about hair, but hair, I believe, is the first technology, if you think about it, because it's actually dangerous, right? No animal, not a single one grows hair as long as humans, because it's very dangerous. And the only reason that we do that is because we cut it. You know, we've rewritten our DNA with technology because we care so much about our hair that we started cutting it, you know, with stones or whatever. And then, you know, that led to us being able to do crazy things with our hair. And it makes sense also that baldness would be part of that story, right? That you know, there's different signaling mechanisms with hair. And it's really, really important to humans. It's very deep in our DNA to pay attention. In the same way that birds pay attention to feathers on each other's heads, and spiders, you know, those little rainbow dancing spiders. I don't know if you've ever seen those, but they're so cute.
Yes.
And, you know, so all the animals are paying attention to something. Humans really care about hair.
Yes. I listened to your 2019, you're talking to librarians in Stanford. That was a important moment for me, believe it or not. That
wasn't it really?
That's when I'm like, this is gonna be big.
I don't know if anybody cared about that talk, but I cared about it. So I'm glad you cared about it.
I cared a lot about it. It echoed in my head for like the rest of the time. But one thing I found super interesting, and this kind of gives you a sense of my quirkiness, is like, here's a guy who's been like trying to think about how to use a GPU single threaded by himself. And he's like, I need to farm this out I need to multi-thread this and have lots of people thinking about how to use GPUs. So I'm going to go to a bunch of librarians and I'm going to like sit here and I'm going to farm out threads right now. Hey, everybody. And you're like you're like the CPU just doling out like threads to all of these librarians, like hoping that they'll all pick it up and go like start their multi-process of like, what data do I have that I could feed this thing? And then obviously the timing's off on this, but you're obviously, that's not the first time you started multi-threading to humans, the innovation of using an NVIDIA chip. But then like one of these threads pops up in Toronto. I'm like, it turns out like a really good, there it is, a really good result. And I couldn't help but think like, if you did that in parallel, like how many lifetimes would you have to live till you came up with that? And
you're talking about Alex Krzyzewski and Ilya, right?
Yeah, like that was just this thread that was spawned from you trying to encourage people to think, to use GPUs, right? For this new, sort of concept. We would call it AI, but at the time it's really just like running parallel algorithm computes, right? For something other than graphics.
Machine learning. Yeah, I mean, really for machine learning. Yeah.
Yeah, for machine learning.
I don't really take credit for Alex and Ilya doing their amazing work. I mean, I feel like we were kind of on parallel journeys, but they did it a lot better than I did.
But I guess more than a CPU takes credit for a GPU's calculation, right? Like you farmed it out without the ability to use a GPU to do it. None of it happens, but it wasn't deterministic, right? You're like,
yeah, and I wasn't the one who made the GPU good for non-GPU things. Like NVIDIA did that. Ian Buck really deserves a lot of credit for that. And
right, that's true. Yeah.
Runs NVIDIA's business. But back when he was a PhD student at Stanford, Ian, built this programming language for general purpose GPU compute. And then he went to NVIDIA to turn that into a product. And that became the beginnings of CUDA.
This episode is supported through partnership with OneReach.ai. Their Generative Studio X platform provides turnkey private architecture and tools for building enterprise-grade agentic solutions. Set up a runtime for AI agents that allows your organization to use any AI models, create customized guardrails, and avoid vendor lock-in, all with enterprise-grade security. OneReach.ai's award-winning GSX orchestration platform meets the many requirements needed to seize powerful new technologies in this pivotal moment. Learn more at OneReach.ai.
My involvement started in 2006 once CUDA was released. And at the time I was trying to do machine learning on FPGAs and other complicated hardware. And I tried it out on CUDA, and in an hour, I had a thing that was running 200 times faster than the CPU code that I was working with, and it was kind of like almost there wasn't any ceremony. It just happened. Like usually, like when I was working with FPGAs, you spend a week writing the RTL, and then you spend another week like compiling it and onloading the bit stream onto the FPGA, and then trying to see if like stuff's going in and out of the chip, and like the process of just like getting the thing to say hello takes like a week. And so I tried this out with CUDA, and I was like, oh, it's faster than the FPGA, and I can't believe like how quick the development process was. It just like it was instant. And so that's when I pivoted, and I thought, GPUs for machine learning could really change the world. I'm going to push on that. So that was in 2006. And a lot of people thought that I was crazy. I remember I published my first paper at ICML in 2008 on training some
And the hair
support
didn't help.
The hair,
Yeah, with them thinking you're crazy. That
could be true. And I was a Berkeley grad student, so of course everyone at
yeah.
Berkeley is crazy
If
anyway.
you shaved your head, they would have believed you more.
That's right. And so I went to this conference, ICML, International Conference on Machine Learning, to present this paper on how to train support vector machines on the GPU. And I actually had people at the conference ask me what I was doing there. They were just like, I don't understand like why parallel computing should matter to machine learning, and I'm not sure why your paper is accepted to this conference. And I tried to explain it as like that, back then, all of the research into machine learning was.
Am I not turtly enough for your turtle club?
Yeah, right. It was all things that people could do on their laptop alone, very tiny data sets. And frankly, the results weren't that great, so I tried to tell people, hey, I think if we scale our data sets, use a lot more compute, these models are going to do a lot better.
Yeah.
We need to pay attention to the systems that are involved. The infrastructure becomes really important if that's the way that this is going to progress. I think it's the case for many of us that, we feel out of place, right? And my research has always felt out of place, no matter what. It always feels like it's caught between two worlds. And I keep telling myself, what a great opportunity. Like, what a great chance to do something that other people aren't thinking about. Because the truth is, when we have these communities, the communities tend to have certain ways of approaching problems and thinking about problems. And if you're kind of an outsider, you have the advantage of the beginner's mind, and you can kind of do something new.
Let me ask you this. This is personal to me. Like, as much as it was uncomfortable, was there sort of a funness about being on a different path than everybody else? And now that everyone's kind of coming over, does it feel less fun in that respect? As everything's kind of moving over to the craziness is the norm, I'm almost finding myself like mixed feelings about everyone agrees with me, but then it's less fun and less different.
Well, I have a couple of thoughts about this. First is that it's fun sometimes to be different, but it's also tough. Like
Yes.
I wasn't getting great performance reviews, and like people, generally at NVIDIA didn't touch it. I was doing this, and I spent like a year trying to convince the CUDA libraries team that they should productize my little neural network library, and they were like, neural nets are old, they're from the 1960s, nobody uses them, and I was like, well, they seem to be getting a lot better, and we should think about helping that market grow, and here's a prototype on how to do that. And it took like a year of doing that. That wasn't very fun. I didn't like that,
Right.
and it felt very frustrating because I'm like, I have this burning feeling about this, and I'm not succeeding at getting others to pay attention. And that changed, and thankfully that changed. But I wouldn't. So being weird isn't always fun. But the second thing is, I think what I miss sort of the freedom that I had of just being able to do whatever I wanted, because it was all small scale and small stakes, and really nobody cared, and I could just do my own little thing. And now everything is so huge, and there's so much attention, and it's like you open the New York Times and there's an article about AI every day, and also the investments. Like, I mean, it is absolutely mind blowing to me that NVIDIA is one of the top 3 most valuable companies in the world. It's just crazy to me, because like when I started this, NVIDIA was worth like $10 billion, right? And now it's worth
Like a
$3,500 billion. It's like incredible change. But what that means is that the world's attention is like, it's like the eye of Sauron, looking at NVIDIA.
Yeah.
It was nicer back when NVIDIA was under the radar, and we didn't have this much scrutiny, in some ways. But in other ways, it actually is really validating to have people care, and to have people listen and believe, some of the things that we've been saying for a long time.
So do you find yourself like sort of from generally trying to go find another thing to be different on, or are you just basking in the rightness of, that's probably the wrong way to say it, but just like, are you just spending so much time?
NVIDIA, I don't know if you know much about NVIDIA, but NVIDIA is not a company that basks. There's no basking. This is like the more success NVIDIA has, the more NVIDIA feels like it's failing. So the amount of stress and conversely, when things are going bad for NVIDIA tends to have a lot of confidence. So it's very counter cyclical. The feelings at NVIDIA are very counter cyclical to the way the sort of outside sees NVIDIA.
It was very entrepreneur like.
Yeah, I mean this is just, I mean we're driven by Jensen Huang. He's the founder of the company, and right. I don't know how many emails from him I get every day. It's usually probably about 30. And, you know, many of them are very specific and very technical, you know, and he's pointing out all sorts of things that we need to be extremely concerned about. So there's like a paranoia, there's no basking, there's no rightness. Everything feels wrong. Everything feels broken. And that's, you know, what success at NVIDIA is like.
Yeah. It's such a meta for dopamine, right? It's dopaminergic, and if you live long enough, you realize that high dopamine, you're like, oh, there's a crash coming. So like, get worried when things are good. Get worried because we're gonna reset here, and then that worry, you know, yeah. To your point, doesn't allow you to enjoy the moment because the goodness is the worry.
We've got so much work to do, but you know, conversely, I do really think that it's one of NVIDIA's great strengths that when times are tough, the company does feel very stable. It feels like we're all on this boat together. We're coming together. You know, NVIDIA isn't a company that does big booms and busts. We don't overhire and then have layoffs. You know, it is a company where we kind of do have this feeling of like, oh yeah, we've been through this before. We'll get through this again.
Got it. So do you find yourself looking for the next way to be weird, the way to be outside, or like, are you looking to stand in a room again and have everyone like look at you with those confused eyes, or are you like, no, once is enough?
Well, I've never been driven by the desire to be weird. What I've been driven by is the desire to have an impact. And, you know, my career has been built on the thesis that compute matters and AI matters. And I think that this is still true, and I'm still pushing it. You know, and I think we've got a lot more to do, you know.
Got it. You're not done. Got it.
I'm not done. I'm still doing the same thing that I've been doing for the past 20 years, and we just have to do more of it now. One thing that like caused me to chuckle quite a bit was all of the hand-wringing in the sort of Wall Street Journal press about DeepSeek. They're like, NVIDIA came up with a way of making AI compute much cheaper. That's the end of NVIDIA's business. And I'm like, you guys, like, so that I felt, okay, I guess I'm weird again because like the Wall Street Journal hasn't like read a basic economics article about Jevons paradox, you know? So I guess it's weird that I have to remind them again about basic fundamentals of like how technology develops. But it's important to me to be able to articulate to, for example, my team at NVIDIA, why are we doing this work and why do we believe that it is going to continue to be important? So that I care about a lot.
Okay. When you talk about the culture at NVIDIA too, it makes me think about some of the ways that we've been thinking about companies needing to kind of reorganize themselves. And I think that idea of like kind of always being wrong and always needing to move quickly, and that there's this pressure to make things better, companies are really going to have to get on board with it as they try to integrate all these tools and like AI especially into their operations. And and I think also that ability, like NVIDIA had to see that there's like this whole other marketplace for what they've created. You know, as companies are sort of creating automations, agentic automations, they might stumble on things that are revolutionary to some aspect of their operations that they weren't even trying to fix. And so I think like keeping that pressure, but also somehow kind of staying open to possibility, is that sort of the sweet spot that you feel like NVIDIA has?
Sometimes, I mean, NVIDIA is not a perfect place. We have lots of failures too, but that's what we strive for. I think it's important for people to understand that there's only one Jensen at NVIDIA. There's only one, and he works in his way. No one else works in his way. That would be crazy, you know? So NVIDIA is not a company, what is it, that holacracy, that idea where there's like no structure, no hierarchy. No, NVIDIA has a structure, and we try to, you know, make it make sense. But at the same time, you know, Jensen brings a lot of agility and flexibility. He's always incentivizing the company to work as one team. And I think actually that's the most important part of NVIDIA. The part that I wish the world could understand better is that the value that NVIDIA brings to the world is in the integration of so many different kinds of technology and business considerations as well. And it really takes people of many, many different kinds of backgrounds working together as one team to do accelerated computing. You know, you think about it, it's like, in order, like what we're selling, the product that we're selling, why should it have gross margins that are higher than a chip? It's because we're selling time and capability to scientists and engineers. You know, they can do things with our computers that they couldn't do without them. That's more valuable than any computer, right? Because there's a capability that comes from it. But what that means is that there's this long chain of things that all are composed together. Like there's chips and interconnects and motherboards and data center designs and coolers and compilers and libraries and frameworks and algorithms and applications. And, you know, there's you know, a gazillion different kinds of work that have to work together in order to provide acceleration. If any one of them fails, then the whole value proposition is gone. And so that so the accelerated computing work that NVIDIA does is really about a full-scale, full-stack optimization and integration, and that requires people to work together. And it is absolutely not acceptable for us to have like the GPU group and the motherboard group and the compiler group, and they all separate, work on their own objectives, and then declare victory. That's not acceptable to us. We wouldn't be successful as a business if we worked that way. And so organizationally, that does require us to work together as one team, which is very hard because humans are territorial, tribal animals, and we don't like working with people outside of our little cone of a hierarchy, you know? And so Jensen is constantly pushing on the company to do that. And I think that's really important.
I was thinking about some of the folks that are working on, like, you know, trying to generate an inference using like more diffusion approach versus word, recursively versus like a more filling in the words. What are your thoughts around diffusion around language?
It's a disruptive idea. So it's very interesting. You know, if diffusion language models end up widely adopted, that has enormous implications for the systems that NVIDIA designs and builds. And so it's something that I'm paying attention to really closely. In a lot of ways, it would be great for NVIDIA, like the parallel properties of diffusion models make it easier for us to design systems to accelerate them. It's a sequential algorithms, accelerating sequential algorithms is generally harder than parallel algorithms. And so we've been pushing really hard to accelerate next word prediction, sequential next word prediction, because that's what currently the world is doing. If the world would switch to parallel, chunk prediction with diffusion models, then that could really open up some interesting possibilities about, how to build the systems for that. That would be really interesting to us, and hopefully also open up some new capabilities. Make AI models much faster, more efficient, and then of course by Jevons paradox, the more efficient they are, the more widely deployed they will be. So that could really grow our market. So it's something that we're very interested in. However, so that was the pro case. The con case is it's pretty complicated. A lot of people have tried and failed, and Google is now reporting some much better results than anyone else has ever seen before, and that's exciting. But there's still a lot of questions about how general it is, how well it could be made to work. And so I'm not going to make the bet quite yet that that's the future of all AI. I also feel generally that sequential algorithms are better than parallel algorithms for reasoning. So reasoning tasks tend to have like really naughty conflicts, and you just kind of have to puzzle through it. And it kind of like this single-threaded nature of that, I think, is somewhat unavoidable. So there may be some tasks for which diffusion language models just aren't really as suited as parallel as sequential ones. But so I'm not exactly sure. I'm not going to make the bet that this is going to take over and everything's going to become a diffusion model.
Yeah.
But I wouldn't be surprised if diffusion language models find a pretty big place in the world, because they do have some really attractive properties.
What do you think about code as the use case? Because functions are sequential, but they're also like, you could create two functions independent of each other without them, depending on each other. That makes sense. Like code is a little less linear, object-oriented code, I guess.
Well, that assumes that you have a good decomposition. So then the question is, how do you get a good decomposition? So maybe like there could be some hybrid modes where you use a sequential language model to like kind of build a skeleton of what you want to do, and then like fill in the skeleton with a diffusion model. Maybe something like that could work. It sounds complicated. I'm curious about with code. I'm curious, is more code better, right? So like, I think with something like image or video rendering, more code is definitely better, right? So like diffusion models, I think if diffusion models are already like widely used for image and video prediction, and diffusion language models being the backbone of future video prediction models, that makes sense to me. But for code, the question is like, how much code do we want? Like, how much code is useful to generate? I'm not sure about that, but I think that's going to depend a lot on the setting.
I was imagining it like creating like 5 functions that do the same thing at the same time, and then something just evaluating like which one, even if it's just like a linter or something, just saying, oh, this one's the best, but then it came down to like, is code as it exists today the best? Or do we invent a new coding language, like almost like an embedding that would make it even more useful?
The interesting thing about code for me is that writing the code is usually the easy part as a programmer. The hard part is figuring out what you're trying to do, and I don't know if you've ever sat down to write some code and then you like import, you're like, what am I going to import? Doing, so it's like you have this like great idea, it's like burning in your bones, you really need to write this program, but then when you sit down to translate it into code, you have to really think more deeply about how you're going to accomplish it. And once you've figured that out, then it's usually fairly straightforward to just like write it. But often that's the bottleneck for me, is being able to translate my ideas from something kind of vague into something specific enough to execute. And I'm curious because I don't actually think that language models solve that problem. I think they can help us explore, but if you don't know what it is that you're trying to do, a language model can suggest some things, but it can't actually decide for you what you want to do. You have to do.
No.
Which means you have to understand code that's generating somehow. And that means you may not want it to have a lot of code, because then you have to read it,
I sometimes like think about cooking, like, hey, I want to make this. Can LLM come up with a list of ingredients? Like, yes, it'll be like apple pie. Now, could it farm out each of those ingredients to say like, okay, GPU, now make each one of these ingredients, right? Now that I've decided the ingredients I need, can I like farm out each? So that's sequential, right? But because I don't need like, multiple types of apples, but then once it's decided, can it like farm it out? And maybe I'm thinking like GPU, CPU is too granular, like it's at a higher level. It's more about distributing work than it is like, you know, at the GPU level.
Like, are there compelling reasons for business leaders to kind of go a little more into the weeds on like CPU, GPU, and like the kind of technologies that are making these things run? And I wonder, especially if like in light of sort of the discussion you and Rob were just having about like, oh, what if diffusion models suddenly become the thing? Like, as a business leader, are you then in a better position if you have kind of a deeper understanding of why shifts are happening at the hardware level and how they're impacting the software solutions at the end?
That's an interesting question, and I don't know how realistic it is for business leaders to pay attention to technology that's developing as fast as AI is, because there's so many ideas. It's a little overwhelming. One thing that I do think business leaders really should pay attention to is administering AI infrastructure. And, if you go to Harvard Business School, you'll probably take some sort of classes about how to lead a team, right? And like organizational structures and like, problems with, people management and like, good practices and things like that. Well, right now, nobody's learning how to administer computers. And that's, I think, a real problem, because actually computers are more fundamental to the progress of AI than ever. And it is the case that if you don't manage your computers properly, then you're going to be starving your teams of the resources they need. And it's where, like, I think HR should know about computers. Like, HR knows about people's salaries. They should know about, and that's an important resource that we need in order to get our work done. But they also should know about how much computing, engineers are getting. And, it's definitely like one of the biggest problems that anybody trying to deploy AI faces is how do you prioritize compute and how do you allocate it? And it's a process that is kind of like managing people, but a little bit different. And I wish more people were thinking about that.
Yeah, I guess there's like a fundamental question of like, how much compute do you need? That's a hard question. Like,
well,
you have to.
Yeah, I mean, if more and more businesses are AI driven, this question of like, how do you project how much compute you need? How do you determine ROI for projects? How do you justify the compute that you're going to be building? And then how do you administer it so that you're constantly reflecting your company's priorities in the way that allocation is done? And then you're paying attention to like, what was the yielded compute, and then what results to get from that yielded compute, and then that kind of informs your ROI calculation for the next cycle.
Right.
This process of like administering and managing compute is really central to any AI driven business, and it's not something that business leaders really think about. And I think if they're used to thinking about people, they should accept that they also need to start thinking about computers.
Yeah. Artificial intelligence is just cognitive capabilities. Then some companies need as much as they can get, like OpenAI, right? Like as much as they can afford.
I would frame it a different way, is that compute is always going to be limited, right? Like you're never going to have enough compute so that people feel like, oh yeah, I can do all the things I want to do, because the demand is basically infinite.
Yeah.
And so that means that you're going to have to accept that your job as a business leader is to prioritize. And your job is to understand the ROI of all sorts of different projects that are clamoring for more compute, and then make decisions about how to satisfy or not the request. And that's a fundamental management operation in the age of AI that I don't think people are prepared to do.
Electricity is a big part of this, right? Like, I mean, at the end of the day, electricity is really Like,
Yeah.
and that's a big
Water.
part of NVIDIA's success, right? Is like the amount of electricity, or the more the efficiency of the chip, right? Not just that it can do this, but in a lot of ways, the costs of the electricity for the chip is, at least the way I understand it, the cost of the electricity of the chip is more important than the cost of the chip.
It certainly puts a lot of constraints on what people can build, right? And people have dreams of building AI data centers that, consume so much electricity that you just can't turn them on. And so it's like, oh, we have a dream. We think it would be really amazing, but we can't actually do it. We've got to figure out a solution to that problem. NVIDIA has been in a completely energy constrained world for more than a decade. I don't know if you've watched Jensen Huang's keynote at supercomputing. It was either in 2011 or 2012, but before AI was big business, and that's what he was talking about. Like, the supercomputing workloads, it's a completely energy constrained environment, and what that means is that every amount of progress we can make in reducing the energy consumption of AI opens up new possibilities to build good AI.
Yeah.
And that's been true. That's been true for more than a decade. So that's like what everybody at NVIDIA thinks about when they wake up in the morning is, how do we make this thing use less power?
Sometimes I think about that. I don't know if I'm thinking in the right trajectory, but when people talk about, AI taking over the world, and engineering level, they're less concerned because they see how simple it is, right? They have a sense of the simplicity, and they're like, how could this take over the world? But there's some part of me that says, well, if you made an AI that could take over the world, I wonder what the electric bill would be and who would pay it.
Yeah.
Like
Yeah.
that is a factor. Like, I think there's the assumption that these things can just run without a resource, and that a GPU just somehow is some sort of flux capacitor. But there's a cost.
Yeah. And they're big costs. I don't know if you saw that Jensen announced at GTC that we're building this 600 kilowatt rack, which, like, I remember when I built my first data center, 5 kilowatt racks were the standard. And I was like, I think we should try to push it to 30 kilowatts per rack. And the data center people were like, 30 kilowatts per rack. Do that. And NVIDIA's like, here's our 600 kilowatt rack, and, 600 kilowatts in that small of a space is an extraordinary engineering challenge, right? But why are we doing that? Well, because it turns out that a 600 kilowatt rack is a lot more power efficient than, 125 kilowatt, right? Because you can reduce the space and the distance that it takes to move information around, which then drastically reduces the power that you're spending on communication. And, so that's one of the ways that we're trying to push power efficiency is by scaling up. One thing that that I think is important is the connections between graphics and AI.
Okay.
And NVIDIA started out as a graphics company, and I think that's because graphics was the first generative compute workload. The first, all information technology before 3D graphics is really retrieval oriented, whether it's like, internet search, or, you want to watch a Netflix movie, or even reaching back all the way to the printing press. All this technology is really about providing access to information. But with 3D graphics, it became about generating, right?
Yeah.
And so, like, the experience that you get from graphics is fundamentally tied to how much compute you can spend in real time to generate graphics. And that's where NVIDIA started this accelerated computing journey. And it makes sense to me that that's where we would start, because that was the only generative workload at the time. These days, AI is the most important generative workload, but it has the same property, right? And that's the reason why NVIDIA started out with graphics, and why we continue doing graphics. We really feel like AI needs
That's
to
so
interact with the
interesting.
and it needs to be able to see, and it needs to be able to generate virtual worlds in order to interact with people and help them solve problems. And so, we continue to push on that. And I don't know if this is true, but I don't know if you've ever used any image or video generation models out there, like ChatGPT's some of Google's. They're pretty amazing. But one of the interesting implications of that, depending on how many tokens are currently being generated around the world in data centers for image and video generation, I think it's pretty substantial. It takes a lot of tokens to make, right? And if you think about what that means, what it means is that NVIDIA has managed to disrupt its main business by transitioning graphics from, triangles to tokens. And that's actually, I think it's probably true that NVIDIA's graphics business is already bigger in tokens than it is in triangles.
Interesting.
And I think that's a really kind of amazing transition.
I also think it relates to what I said, which is diffusion models for text. I'm like, isn't that when you go from text to an image? Like, isn't that essentially like, instead of, so that the picture's worth 1,000 words, like maybe that's what it is when you go from words to an image. Like, why would you necessarily communicate an idea through more words? Maybe that's exactly what's happening. Like, not an essay, a picture.
Or a video. An interactive video. That's where we're going. If you think about 8 billion humans on the planet using AI to do their work every day, most of them are not going to be typed in a box, right? It's just not what 8 billion do. Like some of us humans read and write in boxes all day, but most of us don't. And so I think the user interface for AI is going to be really important. I think AI that doesn't have a user interface is also important, but it's important in the way that electricity wires or plumbing is important. Like you want to not see it and you hope it never breaks, right? But that's not maybe the most economically interesting part of AI, right? Because it turns out, I think that the way that we measure value in our economy is tied to attention,
Right.
And so AI that has no human attention attached to it, I don't think is going to be that valuable. So I really believe the user interface is important, and graphics is going to continue to be really important.
I had this imaginary idea, and I've had it for a long time, but forget the treatments. But imagine I had this pendant around my neck, and it records video and sound and everything, and then I walk down the street, right, and then I could pause, I could open it up, and then I could have it play for me 5 different dimensions of what could happen next. But like where I watched the video of like, you could walk in there and get a donut, but I'm like watching the video as it's generating 5 different versions of the future that I could choose, right? And because it's using the past to generate this future, and now I could decide which future I want for myself based on watching it in a video. Anyway, it's one of those crazy
if everyone
ideas,
has the pendants, then you have like all the context like all that CPU burning context, so that it could actually make predictions about everything around you too.
So reality is like multiplied for every single person as they like look forward and look 5 different versions of what they could do next. Like get a donut and then go to the doctor, and the doctor says stop eating donuts. Anyway,
none of it will involve moving numbers on spreadsheets anymore. So
yes.
I don't know. I still move a lot of numbers on spreadsheets.
Yeah. It's kind of fun. Yeah.
Thinking. Well, this is great. I enjoyed this conversation a lot. I appreciate you having it with us.
Yeah. All right. Well, thanks for hanging out with us again here on Invisible Machines. Don't forget to like and subscribe wherever you get your podcasts. Always remember that you can watch this podcast too on our Invisible Machines YouTube channel. Head over to uxmag.com. We have a podcast page there where you can explore our back catalog, and you can look at episodes centered around popular topics. Many, many thanks to our incredible production team here in the US and in Ukraine: Elias Parker, Michael Litvinov, Allison Harshberger, Alla Slesarenko, Vera Pokodkov, and Darina Moskovchuk. Till next week, Owagi.